Thank you. Since airborne acquisition is a lot shorter than seismic acquisition, I'll probably be able to get to the talk quite quickly. All right, I'm Darren from CGG in Johannesburg, and because I'm from South Africa, there are three problems with my talk today. The first one is that my geophysical background is mostly in mineral exploration, which I hope you guys won't hold against me when it gets to question time at the end. The second problem with my talk is that it's a combination of two case studies, one from Uganda and one from Gabon, and I'm the author on neither of these. So again, I'm quite looking forward to question time, but please be kind. The third problem, which I hope you guys will overlook, is more of a confession, in that even though it says seismic data in my title, I don't have any to show you, I'm afraid. Total and Valco, who we did this work for, haven't allowed us to show any of the improvements that they've made to the seismic data using our airborne data, which I hope speaks for itself in the effectiveness of the work that we've done for them. But I do give the names of the authors, and if you guys do have any questions, I'd be happy to put you in touch with the authors of the case studies in Total and in Valco. So let's get going. The two case studies that I'm going to be presenting are a little different. So it's using airborne gravity gradient data in both frontier and in mature exploration environments. So in this case, the Albertine and White Nile basins in Uganda are an example of using gravity gradient data in quite a frontier environment. And in Gabon, there's a lot of 2D seismic and a lot of well control in the South Gabon basin. And we're using seismic for something slightly different in that mature environment, in mapping out salt and cuvette low velocity structures to help improve the seismic processing. All right, so as gravity gradient is something reasonably new, I mean, it's only really been used commercially since 2008, 2009 for oil and gas exploration. I thought let's get into what it is and why it's used. So there are two different types of gravity gradient technology. One comes from old submarine technology, and the other was developed by BHP Billiton and Lockheed Martin, and it was specifically designed for airborne use, and that's the FALCON system. And it means that the FALCON system is the highest resolution gravity gradient system that's currently on the market today. We've been flying FALCON surveys since 2008. In 2008, 2009, we were only allowed to use the system for oil and gas. However, in 2010, we were able to use it for mineral exploration programs. And obviously, mineral programs are a lot higher resolution than oil and gas. I mean, 5 or 10 times higher resolution. So the BHP system really was designed to collect as low noise gravity gradient information as possible. Just a brief timeline on the two different systems and how they were developed. So in the 1970s, Lockheed Martin developed this gravity gradient system to be used in submarines to help them navigate deep underwater trenches, mainly in the Arctic. And in 1994, that technology was declassified. And in 2002, we actually flew in South Africa some original test lines in Botswana for some diamond exploration using the FTG system. However, we were in discussions with BHP Billiton, and they designed a system purely for airborne use, and we acquired that system in 2008 from them. So this is the difference between the two systems. The original system you can see here has three small instruments that are, they're all located at 90 degrees from each other, they're orthogonal, and it collects gravity gradient tensor components. What BHP Billiton and Lockheed Martin did to try and isolate some of the noise in the system is they created a much bigger horizontally orientated instrument, which can actually fit two instruments on one big rotating wheel. And what this does is it isolates the vertical noise component when we collect data. Even though we don't collect all of the tensor components, we still deliver the same data as the contractors that use the original submarine technology. An advantage of using FALCON is that because we have two independent systems or instruments on our system, we can actually give clients and consultants an idea of what the noise and what the turbulence levels in our data actually is. So flying repeat lines and doing crossover statistics is fine, but they're not co-located, whereas we're collecting two separate independent measurements when we fly. So it's just a way of giving clients and consultants confidence in where the data, what the noise characteristics of the data are. Because over land, you tend to have more turbulence than over the sea, and quite often we're used in transition zone areas where those turbulence characteristics are quite different. And it's worthwhile knowing what you can use the data for in those different areas. We have 5 instruments located all over the world, and we also have one installed in a helicopter system, which we use quite often for very high resolution mineral exploration. It actually gets to the point where we're collecting airborne gravity data that is very similar to the resolution collected by ground crews, but it takes a fraction of the time. A ground survey that could take 6 months can be done in 3 days using a helicopter, and for a low price as well. All right, so the first case study that I'm going to present to you guys today is from Uganda. The Lake Albert area is probably one of the most famous uses of gravity gradient, used in the frontier area. Tullow was very brave in getting Bell Geospace to fly this. I think it was in 2009, and it worked fantastically. The geology is correct for this type of technology, so the targets that they're looking for are 4-way closures, and these respond very, very well to gravity gradient data. You'll notice that the paper was originally given by Anthony Price. I think it was last year at the London EAGE. He gave this presentation. All right, so the geological setting of the Lake Albert region. Lake Albert is over here, and the Albertine Graben sits over here. What happened is they collected data in this area here, which is actually the Pakwak Basin, which is just north of the Albertine Graben, and there's a major bounding fault in that area. And they wanted to see if the same controls that happened in the Albertine Graben, the same structural controls, whether they held true further to the north. Doesn't reach the same depths because all of the faults have a much smaller throw on them. All right, so a couple of aims of the airborne survey. The aims were to try and map the fault system at a similar resolution to some of the 2D seismics that was around. However, the advantage of airborne data is always that you have uniform coverage over the survey area, and it's not like, especially 2D seismic, which only gives you a snapshot of a specific area to look at. We're also looking at the depth to basement and some of the controls on the trapping mechanisms in this area. And Tullow and Total were keen, especially Tullow, because they have a lot of ground in East Africa in the rift, were keen to see if they could use this technique of flying gravity gradient with some regional 2D to focus in some 3D exploration. Would save a lot of time, it would save a lot of money. And so this was a bit of a case study to see if that was possible in the East African rift. So this survey was flown in 2009 by Bell Geospace using the older submarine FTG technology. And it was used as a structural infill between 2D seismic lines. So the 2D seismic would identify a structure, but what happens in the 30 or 40 kilometers in between these lines? And that's where the gravity gradient information was important, to see what happened to those structures in between the 2D seismic lines. Almost all of the structural closures in this area contain hydrocarbons, and these correlate fantastically well with the gravity gradient highs. Another important consideration is that the airborne acquisition is roughly 10% the cost of a 3D seismic over a similar area, and takes much, much quicker to fly. I mean, our surveys normally take anywhere between a month and 3 months to collect the data, which is a lot shorter than the 3D seismic campaign. CGG flew a FALCON survey in 2012, and you'll see, it extends the survey area to the north. It's quite clear to see where that big bounding fault is. And you'll also notice, if I flick backwards and forwards in between the two, that the limits, the data highs and lows in the northern area are much higher and lower, and so they seem to be muting some of the responses here in the south. But that's just because of the big throw of these faults, not the big throw, the extreme gravity gradient response of the geology in the area. So what we did with Total in this case, because Total was a partner in this block, is we planned this slightly differently. We actually flew this at a wider line spacing and at a different line orientation to the survey flown by Bell Geospace 3 years earlier. it was a good test to see how the data would compare, and as you can see, it compares quite well. But it allowed us to collect less data, which is cheaper, and it also allowed us to take care of some logistics complications in the area. There were some security concerns, and so we didn't want to base in certain areas that there were some security problems with. And so it allowed us to do the survey quite quickly and quite cheaply and most importantly, safely. Something that's quite good to notice is just the structural continuity between the two data sets. So collected with two different instruments. Like I said, the data that we deliver is the same, but two instruments of quite different design. And I think the data is quite comparable. Okay. What we did with the data, Total hired us to firstly collect an extension as well as reinterpret the entire data set. So initially we went through a qualitative assessment just to get a feel for the seismics and to what some of the structures in the gravity gradient was telling us. You'll notice this is actually a depth to basement map. So again, there's that big structural discontinuity between the Albertine Basin and the Pakwak Basin to the north. And it allowed the interpreters to build up some confidence in what the gravity gradient data was showing them. We then did a quantitative analysis, and we looked at some magnetic depth estimates as a first input into our inversion process to use the gravity gradient tensor components as well as the magnetic data. And we did a joint inversion on that to get to this depth to basement model, which is quite high resolution. And it also allows us, because it's now a product that's been beneficiated, it's a depth surface, so we can use this to correlate the 2D seismic. We can put the 2D seismic on this and have a look in 3D as to what the depth of the basement is, what the structures are doing, what the geometries of the structures are, and help Total and Tullow plan further exploration in the area. All right, so the bulk of my presentation is actually going to be on using gravity gradient information in Gabon. We did this work with Bain Geophysical and Volco Energy, and again the authors are listed, so if there are any questions, I'd be happy to put you in touch with the authors. And what we did in this area it's a much more mature area, so there's a lot of 2D seismic collected, like I mentioned earlier. There's a lot of well control, so we were using it primarily to try and help map out where the salt was, what the geometry, especially on the flanks of the salt was, because it was causing some issues with the seismic, and as well as identify some cuvettes, which are saucer-shaped low-velocity sediments that can also cause problems with some of the seismic data. It's a passive margin, continental margin type of environment, so quite different to the rift. And here's a general cross-section through the Mutombo Iroru block, which shows I think the Gamba Sandstones are sitting here, and on top of the Gamba Sandstones there's a salt cap, and it's a fantastic seal, but unfortunately the salt has been mobilized and structurally really, there's a lot of structure going through the area, so it's quite difficult to interpret the seismics on the flanks of the salt bodies. As I said, the target here is the Gamba Sandstone, and it's a very nice porous reservoir. It's about 30 to 50 meters thick. The source rock is the Melania Shale, which has quite a high total organic carbon content, apparently locally in some areas as high as 20%. So it's a fantastic source, really nice reservoir, capped with salt. And a lot of seismic in the area, but I'll show you a bit later. It's a really, really difficult area to collect data because it is in this transitional zone between onshore and offshore Gabon. So having a look at the depth to the top of the Gamba, you'll see that there is something called the Varig Robin, which runs through the center of the survey area, and on the western flank is where most of the hydrocarbons are accumulated. Again, we're looking at four-way structural closures, and they're formed on the upthrown block, so slightly closer to surface block. I apologize for the color scale of this. Red is higher than green for a change, but I think we can all see that this upthrown block here is where most of the hydrocarbons are accumulated. exploration history in nearby fields. You can see there's a lot of work that's been going on. There's a whole lot of wells. There's production happening in Gabon. So this really is a mature exploration environment. And we did this survey in 2009 again. And it was in an environment that was quite well understood. The stratigraphy was well understood, but both Valco and Total wanted to get a better idea and wanted to try and see if they could reuse and reprocess some of the seismics to direct some of their brownfields exploration in this area. So there are some of the wells that have been drilled in the area, and it's quite a large area of 1,000 square kilometers. So you'll notice that it is right on the shoreline, and it's very difficult to collect new seismic data, which is why it was worthwhile trying to beneficiate the old seismic data that was available. Some traces of the 2D lines, and you can see there really is a lot of 2D. I think sorry, I was going to. So statements of the problem. We're looking for low relief four-way structural closures, and trying to image that top of the Gamba is quite problematic due to a number of reasons. So the Zanga salt, which is actually the seal, has mobilized in some areas, and there are pillars and diapers and steeply dipping reflectors that can cause some issues with seismic processing and seismic interpretation. There's also a carbonate facies that sits above this, and complex velocity models in that the thickness of this carbonate is not well understood in the seismics, and sometimes there's not a big velocity change between the Zenga salt and the Medela carbonates, and so if there's not a big velocity change, it's very difficult to image that horizon. However, there's quite a big density change, so we were able to image that with the FALCON data. There are also superficial cuvettes, which create statics issues, and we were able to map some of those features out with the FALCON as well. So really quite a lot of different aspects of this area that gravity gradient data can help seismic. So it's really a seismic support tool in this case. So what we were trying to do with the FALCON data was delineate the basement surface. It's always worthwhile to know what's happening with the basement, and then figure out what's happening with the complex geometry of these salt bodies. What we did is we did some forward modeling, and the resolution of the FALCON data was 150 meters, and it certainly, with our noise floor sitting generally below 5 ETVOS, the response of these salt bodies would be well above that, so we should really be able to map out the salt bodies correctly. So it was a 6,000 line case survey, flown in 24 flights. It took us just over a month to complete this work, so really not a long time. And this is the area we flew over, so you can see it really is very, very, very difficult. A lot of these islands, a lot of transitional zones, a lot of swamp. You really don't want to be collecting a random, unfocused 3D seismic in this area. So that's why we were asked to come in and see if we could help with the 2D seismic data. So we collected the data and went through 2 interpretation phases. And unfortunately, Valco has said I can only present the regional phase, and the prospect phase we're not allowed to show. But I urge you, if you do see John Bain or if you see Howard Cornelius from Valco at any conferences, please do ask them about the success of this project. So here is some gravity gradient data, vertical gravity gradient data over the survey area. And it highlights a couple of things. It's very strange looking data in that you get all these worms, all these lows across the area, and those represent the salt and cuvettes. So we expect them to be density lows, and they show up as gravity gradient lows. We also get the near basement surface shows up, but they show up as these gravity gradient highs. So you can see the sediment thickness gets a lot thinner as you go further to the onshore. We're also seeing evidence of the weak overprinted Varig Robin in this case, as well as these horsed uplifts. So these uplifted areas are some of the features that Total and Valco were interested in and trying to, they were the most prospective and trying to make sure we image the salt flanks over those areas. This is an even stranger looking image, and it's the horizontal gradient of the FALCON image, FALCON data. So what it shows is the flanks. It highlights the flanks of the salt area. So all of these red lines, red and white lines here, are actually the flanks of the salt bodies. And by using this data, we can help reprocess the seismic data to get better definition of what the salt's doing and what the resource underneath the salt looks like. Again, we generally start with a depth to magnetic basement, and we input that into our inversion process. We produce some lineaments, looking at map products, and then we produce a 3D surface that we use to start our inversion process. So what we're looking for here is the top of the Izinga salt formation, and after the inversion, we can see what the top of the salt formation looks like. So we know what the basement looks like, we know what the top of the seal looks like, seeing what these salt bodies do, and we input this into a seismic processing workflow, and out of that workflow we can beneficiate that 2D seismic data. What was very nice about this work was we flew this actually in 2009. A couple of years later, Total drilled a hole, or Valco drilled a hole, sorry, and they drilled a new discovery hole. So this was an area that was quite well explored. There was good well control. There was a lot of 2D seismic. But taking that 2D seismic and using some FALCON data, Valco were able to redefine and rethink about some of their strategies in this area, and they discovered a new resource. All right, so some conclusions about the Gabon data is that it quite clearly delineated the outline of the salt in the cuvettes, and the seismic depth conversion was unreliable, but we were able to make a higher resolution velocity model, something that was based a bit more on reality, and seismic data was improved. We looked at the geometry and relative thickness of the Izinga salt formation and the near-surface cuvettes, which again helped the interpretation of the seismic data. Something else that was interesting is that a cross-plot of the Bugay gravity versus the salt thickness actually proved to be quite reliable when Valco drilled some of these wells into what the salt thickness was. So probably quite a local effect, but it was a nice surprise in that you can, in this case, use gravity as a predictor of how thick that seal was in the area. We did a depth to basement using the magnetic data and inverted that using all of the gravity tensor components, and we got a much better understanding of what the petroleum system in the environment was, and that helped locate a new discovery hole. So not only was this useful in an exploration phase, but it also was useful in helping to drill wells and predicting what the thickness of salt should be in wells. So quite useful throughout the entire exploration phase, which is very nice. So I think this really was quite a successful result, and hopefully once Valco has matured in some of the exploration endeavors in this area, we will be able to show some of the seismic data, but that's not the case currently. So I'd just like to thank Valco and Total Gabon for allowing us to show this work. And just the last note is gravity gradient data can generally be used throughout the exploration cycle in both frontier areas and mature areas. And I urge you to stay to the panel discussion at the end, where John Siegfried from Archex will give us a better overview of how gravity gradient data has helped petroleum exploration in Africa. Thank you.
Very good. Okay. Any questions? Please, over there. And please say who you are and where you're from.
And let's remember we're hungry.
Yeah, Phil Birch from Impact Oil and Gas. Yes, I'd just like to ask, is this technique water depth sensitive?
Yes, I mean, the further you get away from your target, the smaller the response is going to be. With any gravity technique, you need to know what the ground surface is like. So when processing up the gravity, we'll do a correction for the bathymetry as well as for the salt water. So we're flying this in an aircraft, normally 80 meters or 100 meters above the ground or the ocean. But if you're flying in 3 kilometer thick water, you're 3 kilometers away from your nearest source. So absolutely, it is luckily with CGG, we have many different gravity technologies. So we have FALCON, which does the really high resolution stuff, 150 meter type wavelength. We have standard gravity as well. You want to look down at 3, 4, 5 kilometers. We've got something that's a bit cheaper to fly than FALCON, and we'll fly much wider space surveys for you. So one of the advantages of using a CGG is we'll be able to forward model your geological problem, figure out what the best, cheapest way is to do what you want to do.
Thank you very much.
Because it's quite deep off Durban, I imagine.
Anybody else? Okay.